Hello, my name is Cecilia Reed, and this is my fourth lab report for Physics 2212 regarding the relationship of voltage, resistance, and current. The purpose of this lab is to observe how voltage, current, and resistance interact in ideal or simulated environments. I first went through the simulation trying different situations and then used the data to calculate the RC value for the simple RC circuit. The major concepts that allowed us to calculate the results of this lab were Kirchhoff's loop junction rule and the principles of voltage equals current times resistance and the various iterations of that equation. Using these principles and after graphing my values, I found the RC to be 6.9 seconds. Here are the concepts one more time. To begin the experiment, I navigated to CCK, which was given to us in the instructions, and simulated the first circuit shown. I observed that the currents of I1 and I2 were equal in magnitude. I then replaced my ammeter with a voltmeter and observed that the current was equal to 0.15 amperes. The lab asked us to evaluate what would happen if the ammeter connection was reversed. When the when the connection is reversed, the current is equal in magnitude but negative to the original current. It read negative 0.15 amperes. Next, I replaced the ammeter with a voltmeter. The observations from this portion of the procedure were again that the voltmeter caused the current to be that the reading from the ammeter became negative. Replacing the ammeter with the voltmeter caused the current to be reduced to 0, since the voltmeter does not actually conduct current. The voltmeter read 3 volts because it was measuring the potential energy difference with the ground rather than that of the circuit. Next on the procedure, I replaced the voltmeter with a wire and measured resistance A through H with the voltmeter. A through B measured negative 3 volts, B through C measured 0, CD measured as 0.96 volts, DE was 0, EF was 2.04 volts, and FG and GH were 0 volts. The total volts all summed to 0, which fell in line with Kirchhoff's rule for the round trip of the circuit summing to 0. The voltmeter did not ultimately affect the current because voltmeters have infinite resistance, so no current flows through. Next, I connected an ammeter in parallel circuit with a 100 ohm resistor. Both currents read 0.06 amperes instead of the normal 0.15 because the current was effectively split. Kirchhoff's junction rule explains this phenomenon as the current is effectively split between the ammeter and the resistor in parallel circuits. The ammeter also has no resistance, meaning that the current only flowed through the 46 ohm resistor. Calculated resistance for the 46 and 100 ohm resistor is shown at the bottom of the slide. Finally, I set up the following circuit and connected a 9-volt battery to a 10-ohm bulb and a 200 mF capacitor, which caused the light bulb to shine. When T was initially greater than 0, the capacitor was charging and the bulb was dimmed, as the current ultimately slowed down. When T was much greater than 0, the capacitor had finished charging and the bulb had turned off while the current stopped flowing through. I then disconnected the battery and connected the capacitor to the light bulb. The light again shone bright while the capacitor discharged. As time was initially greater than 0, the bulb began to dim as the current began to slow down. As T was again much greater than 0, the light eventually extinguished as the capacitor fully discharged. The charging time and the discharge times of the 20 ohm bulb were twice that of the 10 ohm bulb, which made sense as the resistance also doubled. The last part of the procedure involved setting up a 9-volt battery, 200 mF capacitor, and 30 ohm bulb. I measured the voltage across the capacitor with the voltmeter and set up the capacitor to discharging. I used this data to plot 20 seconds worth of voltage versus time data. As seen on the graph, the natural log of V decreased with respect to time, which made sense as the capacitor was discharging over time. The equation of the graph in the form seen below allowed us to determine that the slope was equal to -1 over RC, which can be easily calculated. Ultimately, RC came out to be 6.9 seconds, which is extremely close to the simulated value of 6 seconds. What if we were doing this lab in real life? Real-life ammeters have a small amount of resistance as opposed to the simulated ammeter, which has the ideal net resistance. The small amount of resistance in real-life ammeters causes the current reading of the circuit to be slightly smaller than it would be in a simulated situation. What if we had used a real battery? If a real battery was used to charge the capacitor without a resistor, one might predict the capacitor would be fully charged instantly after being connected. However, small amounts of resistance in real-life circuits mean that it will take a little bit longer than instantaneous charging to charge the capacitor. Thank you for listening, and I'll be back for Lab 5.